So, what are they? Well, they enable machines to understand and interpret human language by representing words as vectors in a continuous space, a bit like mapping out words in a way that captures their meanings mathematically. In this segment, we'll explore the fascinating world of word embeddings. We'll dive deeper into their role in deep learning, how they're derived, and the implications of the distributional hypothesis, which suggests that words with similar meanings tend to appear in similar contexts. So stay tuned as we unravel the intricacies of these powerful tools. It's going to be an insightful journey. So far, we've learned about the importance of word embeddings in natural language processing, focusing on the word-to-vec algorithm. We explored how these embeddings represent words in a dense vector space, capturing semantic relationships and allowing us to detect contextual similarities. We successfully implemented both the skipgram and continuous bag of words models to find words similar to our target word, king. Additionally, we visualized these clusters of word relationships using dimensionality reduction techniques, while also discussing the limitations of traditional embeddings, which ultimately led to the development of contextual embeddings. Now, let's dive into how these embeddings work fundamentally and take a closer look at the mathematics and algorithms behind them. Let's start by digesting the distributional hypothesis a bit more. The idea that words appearing in similar contexts tend to have similar meanings can be illustrated through a simple example. Consider the words king, queen, prince, and princess. They frequently co-occur in contexts related to royalty. By representing each word as a vector, we can analyze the spaces these vectors occupy. The closer two word vectors are in this space, the more related their meanings are presumed to be. Now, let's implement the following code to install the GenSim library, which is essential for training our word-to-vec model. We begin by using pip to install GenSim, ensuring we have access to its robust functionalities. After installation, we will import the necessary classes from the library, specifically the word-to-vec class. Next, we'll prepare our simple dataset of sentences, where each sentence is represented as a sublist containing words. This dataset includes our target word, king, and illustrates the relationships we aim to capture. Now, let's see how we can train the word-to-vec model with our dataset. By calling the word-to-vec class with specific parameters, we control various training aspects. The vector size parameter determines the dimensionality of the resulting word vectors, while the window parameter defines the maximum span from the current word to the predicted word within a sentence. The min count parameter allows us to filter out words that appear less frequently. And by setting SG equals 1, we indicate that we want to use the skipgram model. This setup lays the groundwork for creating meaningful word embeddings that encapsulate the contextual semantics of our words. Next, let's dive into the code that will help us retrieve and visualize the word embeddings for our chosen royalty-related words: king, queen, prince, and princess. To kick things off, we'll pull the vector representations of these words from our trained word-to-vec model. Each of these words can be accessed from the model's word vector storage using its specific key. This allows us to conveniently store these vectors in variables for later use. Now, to really grasp what these vectors look like, let's print them out. By displaying the vectors for king, queen, prince, and princess, we can visually examine how close or far apart these vectors are within that high-dimensional space. This visual insight is crucial. It lays the foundation for what comes next, calculating cosine similarity. After we've retrieved the vectors, we'll move on to implementing a function that calculates the cosine similarity specifically between the vectors of king and queen. This function will compute the dot product of the vectors and normalize it, essentially scaling it by the product of their magnitudes. The outcome is a value that tells us how closely related these two words are in the embedding space. That similarity score will serve as a quantitative measure of the relationship between our royal terms, reinforcing our exploration of the distributional hypothesis. The displayed bar chart titled Cosine Similarity Between Royalty Word Embeddings shows 4 bars representing the words king, queen, prince, and princess with cosine similarity scores of 0.90, 0.88, 0.85, and 0.80 respectively. Key patterns are already showing themselves. We see that king has the highest similarity value at 0.90, closely followed by queen at 0.88. Then we have prince at 0.85 and princess at 0.80, forming this nice descending sequence. The numeric labels on each bar really make these small but significant differences clear. From these values, we can conclude that the embeddings position king and queen very closely together in vector space, which lines up with the distributional hypothesis. This suggests that words sharing similar contexts tend to cluster together. The gradual drop from king to princess indicates that overall, male and female royal terms are all gathering around the same semantic region, though with slight separations. These could reflect differences in how they're used contextually or even how frequently they appeared in the training data. Practically, this suggests that if we're conducting nearest neighbor searches or clustering, we would likely retrieve queen and prince as strong associates of king, while princess would be somewhat more distant. Plus, those small numeric gaps in cosine similarity could really help guide our threshold choices for tasks like semantic search, analogy solving, or even grouping related terms. Now, let's implement the necessary steps to get contextual embeddings using BERT with the Hugging Face Transformers library. First, we need to install the Transformers library, which is super important because it gives us access to pre-trained models and tokenizers. Once we have the library set up, we're going to import BERT tokenizer and BERT model, along with Torch for our tensor operations. Next, we'll load the tokenizer from our pre-trained model. That's going to convert our input text into a format that BERT can understand. Essentially, it's transforming words into token IDs. After that, we'll instantiate the pre-trained BERT model itself. With our model ready, let's tokenize an input sentence that includes our target word, bank, ensuring it returns the data in tensor format. This is crucial for what comes next. Now, it's time to perform a forward pass through the model to obtain those embeddings. We'll wrap this operation in a no-gradient context using torch.nograd, which is really useful for saving memory and computational resources during inference. Finally, we'll extract the output from the last hidden layer of the model, which contains the embeddings for each token in our input sequence. This output provides us with rich contextual information to work with, setting the foundation for advanced NLP tasks. Now, let's implement the following code to extract the contextual embedding for the word bank from the last hidden states output of the BERT model. We achieve this by indexing into the last hidden states, which contains embeddings for every token in our input sentence. To access the specific embedding of bank, we utilize the input IDs generated during tokenization. In our case, the index corresponding to bank is 2. We're going to slice the tensor using this index, which allows us to extract the relevant embedding while considering its context within the sentence. This is crucial because contextual embeddings adapt to varying usages of words based on their surroundings, enhancing their relevance for tasks like sentiment analysis or question answering. When we print the resulting bank embedding, we can examine this dense vector that represents bank with all the nuances imparted by its contextual placement. And this illustrates how contextual embeddings provide more semantically rich representations compared to traditional fixed embeddings. This flexibility is key in demonstrating how modern NLP models understand and process the complexities of language effectively. In conclusion, word embeddings really transform our approach to language processing and deep learning, enabling us to derive meaningful relationships from textual data. We've explored the foundational concepts surrounding word embeddings and implemented word-to-vec through Gensim. Then we stepped into the fascinating world of contextual embeddings with BERT, which is a game changer. As you continue learning, keep in mind that understanding the nuances of different models and their applications is super important. Word embeddings aren't just a stepping stone to more complex assignments in NLP. They really enrich our models with deeper language understanding. Next time, we will delve into how these embeddings can be harnessed to build sophisticated AI agents tailored for specific tasks. Thank you for joining me in this exploration of word embeddings in deep learning. Happy coding!